All right, welcome everybody. We are live finally. Thank you so much for taking the time to watch a couple of our first videos to help you get a nice introduction to what this training is all about and to sort of see what we're trying to cover. This session is a little bit more hands-on. We're going to be diving into some of a little bit more of the nuts and bolts and actually doing a little bit of coding on this and sort of going through the decision problem that we highlighted in the previous video. But before we really get going, I know some people are probably going to be coming in here and there, so I'm gonna ramble for a minute just to make sure that everyone is starting on the same page. So a few things I'd like to talk about before we dive in. There are a lot of people registered and a lot of people attending. So definitely take the time to submit questions and thoughts and things like that. But for questions, definitely use the question and answer tab within Zoom. That'll be the best way for the folks on my side that are helping out to help answer any questions that you may have during this session. So definitely make sure to utilize that as much as you can. Again, there are a lot of people, so have a little bit of patience with your questions. If we don't get to it right away, we're working to answer as many questions as we can, as quickly as we can. And if we don't get to your question by the time this session concludes, feel free to repost it in the Whova app. And we'll get to it eventually and make sure that that you're all satisfied and good to go. Let's see. So I will be using Google Colab for the modeling exercises, and I suggest that you do so as well. I think it's a cool way to experience sort of the notebooks. If you want to make sure, and we've hit on this a few times, but I just want to make sure that everyone is good to go. If you want to run the notebooks, actually execute cells in Google Colab, you need to make sure that you are signed in to a Google account. If you are more comfortable with Jupyter notebooks, the old IPy notebook file format, and you have Jupyter ready to go, Anaconda, and all that sort of stuff, feel free to download those notebooks and go for it that way as well. You may need to do a quick pip install of gurobipy, and that'll give you a very small temporary license for running these notebooks. So I hope that answers a lot of the questions that you may have had sort of hopping in right away. So without further ado, let's get going. So as I mentioned in the previous video, let's translate a decision problem to an optimization model. And I gave a quick introduction to what that decision problem is. And that decision problem is, all right, we have a bunch of facilities that make widgets. I like using the term widgets, my favorite sort of go-to term for these types of examples. But so we make widgets and we need to distribute them. We make them in particular facilities, and they need to be distributed to other locations for further distribution down the line. But we're just sort of considering this sort of manufacturing to sort of one step out from that. So I gave that quick introduction to that problem. So a few other things that we talked about in that video that I want to just sort of bring to the forefront of everyone's mind are some of the few key concepts of mathematical optimization. The first that we're going to talk about in this notebook are the parameters. And these, again, are sort of the fixed numbers of an optimization model. They're the constants. But these are the things that, as I mentioned before, that are where machine learning, deep learning, and all the predictive analytics that you may be doing, perfect opportunity to estimate those parameters using machine learning. After that, we have our decision variables, and we talked about some of the differences there, what you can have with continuous versus integer versus binary decision variables, and what they sort of are used for. And we'll talk about that a little bit more here. Constraints, these are your limitations on things. and budget constraints, production constraints, people constraints, all sorts of things. And and it's not just those types of sort of business constraints that you may have, but as we'll see as we sort of progress through this example and other examples, that when you need to start modeling things like complex logic, those things are constraints as well, to make sure that the system that you're sort of designing in the model represents the system that you actually have, represents your real life sort of problem that you're modeling. So one thing that I'll highlight here is if you're in the notebook yourself, definitely right click this documentation and open in a new tab. That is a great way to have some of the functionality, some of the functions and commands that we're going to be using sort of on another tab, another window or something like that, so you can check them out. And there's a lot. You're going to see a whole bunch of, model.all, whatever, a whole bunch of things. Don't worry about all that. We're going to probably be using just a couple of those, a few of those. But there, it just sort of shows the full functionality that that you have at your fingertips once you start using gurobipy. So back to the decision problem, we make widgets that we're going to, the problem that we're going to model. We make widgets. We have a set of production facilities that produce these things, and we have distribution locations that distribute those things for sale. Each distribution center has a forecasted demand. So this is something that you would produce with the machine learning forecast, a time series forecast, some type of statistical analysis, or any type of data analysis can work. Again, like I said in the previous videos, you don't need to be a predictive analytics expert to use optimization modeling, to use mathematical optimization. You can use this type of modeling no matter where you are, sort of in that sort of analytical maturity curve that a lot of people like to show. Each facility has a min and a max number of widgets that it can make during a period. And we also want to make sure that we produce enough and send enough to the distribution centers that we're actually meeting demand. So how I sort of set this notebook up is, let's look a little bit into the math notation, that fun stuff that hopefully it wasn't too crazy to digest if it's new to you. And a quick note on that is, if some of the notation, like the set notation that I sort of discussed a little bit, if that is, like, that I don't quite get that, or, it's not it's not essential to understanding optimization modeling. It helps understand people's formulations, and it's sort of a common way of writing these things out. But again, it's not, not a make or break type of thing. So the way that I designed this notebook is, let's have a little bit of math, and then let's sort of relay that directly to the code that we're going to be using in this notebook, and just sort of just common practice. Again, you don't necessarily, when you write the code for these things, you tend to be a little bit more descriptive, and in your formulations you try and be a little bit more concise in how you write things out. So here are our two sets. We have our set P, which is our production facilities, Baltimore, Cleveland, Little Rock, Birmingham, Charleston. I'm a Cleveland native. That's why that guy's in there. And distribution centers, Columbia, that's South Carolina, Indianapolis, Lexington, Nashville, Richmond, and St. Louis. These, chose these cities kind of at random. So that's our two sets, and we're going to call set P production and set D distribution. You can sort of see on the right-hand side here. And as is common practice, and we sort of seen this through some of the formulation that I posted in the previous video, that we'll use capital letters for our sets and the corresponding lowercase letters for the index of each of those, which represents the individual elements. So, all right, first bit of code. Run this cell, and even though I already did, and it has a little check mark, oops, I gotta run. There we go. You'll see this stuff pop up here, looking for requirements and all this sort of stuff. And I've already did the quick pip install of gurobipy. If this is your first time doing that, it'll take a second. There'll be a couple, a progress bar, and some stuff will happen. It might take, 15 to 20 seconds, something along those lines. but eventually it should be, you're good to go. And it'll say something about a license that expires in 2 years. Essentially, what this license does, what it enables you to do, is it enables you to solve problems that have a very restricted number of decision variables and constraints. So perfect for learning in instances like this. The other packages that the main package we're going to use is pandas, and then importing that in gurobipy. So here we go. Here's a little bit, I decided to put the sets, production and distribution in a nice little list here. And again, if you're not super familiar with some of these Python constructs, again, it's not super make or break, but it's how I'm going to present the material for now. So we have our sort of introductory stuff here, imported some packages, defined some sets. And this is, I want to highlight this here. This is the line that gets everything going in terms of optimization modeling. It is our GP for gurobipy.model, and then a name of the model that we're going to put in there called widgets. And we want to set that as an object. We're going to call it M. Call it whatever you want. Call it widget model, call it whatever you'd like. But I like a simple M because you end up typing this a lot. So I like to make it short. So the parameters of this problem, we talked about what these things are in some detail, but again, here's a little bit of the math. We have MP or M sub P, if you like to use that little type of, if you want to talk about it like that with a subscript. That is the max production that we have at a location P for every P in our production set. And we're going to call that max underscore prod in the code. And then N sub D is the number of customers for a distribution center, D for all of those guys there in our distribution set. And that is N underscore demand. And then we have the cost, the pairwise cost between each production facility and each distribution center. And that is going to be, actually, I already made caught my other a typo here. I changed it to trans cost. So it's not just cost as we see here. It's transportation cost, because I wanted to become a little bit more descriptive here. If you wanted to add other costs, then it may get a little confusing about what you're talking about. So there's transportation costs. There may be things like, site development costs or costs that relate to the bits and pieces that make up our widgets and how much those things cost. So it's good to be descriptive there. And that's why I made that little change. So we're going to read in a CSV for that cost data. And it's nothing too complicated. The cost data itself, just a pairwise, for every production facility, every distribution center, here's a number. And let's run that here. So in order to make it look a little bit prettier and to see it a little bit more nicely from a visual perspective, pivoted the table here so we could see what our costs are between each of our production facilities going down vertically and our distribution centers going across each column. So this gives us a sense of what the costs look like for producing in Cleveland and sending to Lexington is going to cost 2.54. We'll call them dollars, but this could represent thousands of dollars, or it could be any type of I was a little vague here on purpose, just because this is a nice little toy problem to get us going. After that, we have our actual parameters for production and demand. So let's run this, and we see. This, I just decided to do some good old-fashioned hard coding just for fun. Although, typically this wouldn't be another sort of CSV read-in or something like that, some, reading in the data from some external source. But I left it like this in case you wanted to make quick little changes to some of the, while you're sort of experimenting with this notebook. If you want to make quick little changes, what if I change the production from this to this, or the demand from this to this? This makes it a little bit easier to do so quickly, as opposed to going to a CSV, opening that guy up, making the change, saving, re-importing. That there's a couple extra steps there. So this is what our max production looks like. with Baltimore, Cleveland, Little Rock, Birmingham, and Charleston having these max production values. And let's also take a quick look at the demand we have here. So Columbia, Indianapolis, all of our distribution centers. This is our anticipated demand that we'll say was developed using a really awesome machine learning model that has next to zero error by you. And says that everyone can see my screen. And let's move this out of the way. Okay.
Confirming that we can.
Oh, thank you. Well, okay. Yeah, for some reason, the power in my house flickered. I think it's windy outside, which even if it's windy outside, that's never happened before. But of course it happens now. All right. So let me back up a quick minute because I probably cut out a little bit earlier than I thought. Let's start at the parameters. Here's our cost parameter. There we go. Here's our parameters for production and demand. I think, I showed those probably right before I cut out. And then I started talking about the max output and how that relates to our minimum input that is part of our business problem constraints. So we're going to set that as at 75%. So what that's saying is, yeah, we have, a facility can produce, Cleveland can produce 200 widgets in a period, but it also must produce 75% of that. You could definitely make these, specific lower bounds. I just chose a blanket 75%, to make things a little bit easier for now, but, you can definitely set lower bounds that are unique to each individual production facility if that's what you think would be more realistic for your problem. So the decision variables, this is what the output is. This is what we're looking for. This is what optimization modeling is all about, is we want to get these values. And we talked about each of those individually before, what a continuous decision variable is. Something like a price of a product is an example. Integer, the number of food trucks, and we're going to get into food trucks a little bit later tomorrow. And then binary yes or no decisions. These are sort of understanding the alternatives of your options. So these are, yes or no, am I going to include a certain stock in my portfolio? I'm running a portfolio optimization problem. You need to make those choices. So it's sort of yes or no, am I going to do this? So let's see. The decision variables and parameters, we're indexing those using the elements of the set. So again, P represents production, D is for distribution. So we're going to define our decision variable. So essentially we need to think of what is the decision that we're trying to make. And in essence, we're trying to decide on the number of widgets that should be produced at facility P and shipped to location D. So that is our decision variable X sub PD. So now we have our decision variable. And you could think about, well, which one of the above does this really, which one of the above should this be? And we'll talk about that a little bit more down the road, a little bit later in this notebook. But let's start actually adding these things. Let's start actually typing stuff. That's fun. So here's how we add variables in gurobipy. There are two main commands to do so. One is add var and add vars. You see the difference there. There's an S in the latter, and in the former there is no S. So this add var adds a single variable at a time. Add vars adds a group of variables according to some set or index. Definitely right click the add vars one, have that open as well, so you can check out the open a new tab, check out the documentation there. So and with a lot in the case of pretty much writing any type of code for anything, there's always different ways of going about it. There's different ways to accomplish the same thing. And there's, coding in gurobipy, same thing, same idea happens there. So there are a few ways to go about adding these decision variables. So one is you can and this is something what may have been your first intuition of how I would want to do this is, okay, well, if I need to add a decision variable for each production location, each production facility, each distribution location, let's loop through all of those and add a decision variable. And that is something that's what we can do. So let's define our variable X like this and say, okay, let's open up a little, this is where we're going to stick them, our variables, and we're going to have for P in production and for D in distribution. And 4. There we go. We're going to say XPD, which is our decision variable, as we can see right up here. It's going to be equal to, all right, so we're going to set this here, and we're going to reference the model that we want to add the decision variables to. So m dot add bar, and then what this is going to do is just going to add a variable, and then we can also name it to give it a more descriptive name, so we could see, and we'll see where these pop up in a little bit. So we're going to give this a name of, since we're looping through all of these, we're taking a production facility, and then let's do this. So this is going to say, it's going to pop out a text string from P to D. So from a production facility to a distribution facility. And then when we run this, there we go. Our variables are added. So let's see what it looks like. And this is something that will pop up pretty often when you want to look at what sort of pops out of this. It says awaiting model update. Perfectly fine. Essentially, even though we added it to the variable, or we added the variables to the model, we need to tell gurobipy to sort of update everything. So we do m update, and then we'll run through all of this. And now we see for Baltimore and Columbia, for this pairwise, we have a variable from Baltimore to Columbia. So this is one way of doing it, just with for loops. And another way is to give gurobipy the sets that you want to make each decision variable for. So out of the interest of time, since I got cut out a little bit, let's just copy paste here. And let's print this again, just to make sure that we have the exact same thing in terms of the indices here, Baltimore and Columbia. But what happened, the name comes out a little bit different. I chose the name prod_ship. So it sort of just adds the text of the indices to the end here. So it looks a little bit different, but functionally exactly the same. And then the last one other way to do it is, well, we already have this relationship of production facilities and distribution locations. We have that relationship in our cost data. So why don't we just use that set of indices as well? Oops. So we can do that as well. So our transportation cost index, again, is going to look pretty much the same as this. And we're going to call it the same name as before. And these two are exactly the same. So again, that m update command, you don't need to run it you don't need to run it every time you do anything. I just ran it here just so we can see these names and things like that. So now that we have our decision variables all nice and coded up, let's look at our constraints. So adding constraints is very similar to adding variables. It's the same type of command. You can add one at a time with add constr. You can add a bunch of them using add constrs. And it took me a little while, as I was getting more familiar with gurobipy. Sometimes I just make the mistake of forgetting the S or keeping on the S. If you get an error about that, like saying, oh, I added the constraint, I'm pretty sure everything I put in there was right. Just make sure that, if you wanted to add one constraint at a time, that you have the, no S, and if you want to add multiple, that you do. So let's look at our constraints for the decision problem we have. So the first one that we'll look at is we want to make sure that we can meet demand. So essentially what we need to do is we need to take all of the production facilities, add up everything that they produce, and not just add up everything they produce, but add up everything that they produce that is supposed to go to each individual distribution location. So we sum over P for production facilities of our decision variables, XPD, and we're saying that summation, so everything that is being sent to a particular distribution center, add up all of those values, and all of that needs to be greater than or equal to the demand that we have at that particular distribution location. So this will be the first time that we look at what we have. What we have as the quick sum functionality in gurobipy. There are other ways to sum expressions in gurobipy and in Python and everything. There's always multiple ways to do stuff, but I'm going to focus on using this one. It's not the most concise to code. It's not very compact. You have to add maybe a little bit more, but it is easier to sort of see what's going on. So, so let's create a constraint called meet demand that uses the quick sum functionality and that models the constraint above. So meet demand. And let's say that's going to be equal to, and again, just as we sort of say we want to add this to a particular model M, we do M dot add constr. And I'm going to be just adding many constraints at once. This is way more common, at least in my experience, but to add multiple constraints at a time. And hey, even this stuff pops up. So if you get a little lost about what's happening, this little bit of information can help out. But so essentially what we're going to look at, what we need to add in first to this constraint is what we call a generator function. And that generator function needs to be completely in parentheses. So essentially what the generator function represents is we need to code this whole statement into one chunk of code, one bit of code that's all contained in parentheses. So to reference the quick sum function, we need to do GP quick sum, and that is going to be we want to sum over our decision variables XPD. And what we put here now, right after the decision variable, is we immediately put what we're summing over. And so we are summing over the index P. So we want to sum for P in production. So immediately after the decision variable, we put P in production. So that essentially what this part represents here, this first set of parentheses represents kind of what's on the left-hand side of our inequality. Close that parenthesis, and then now we put the operator that we want, or the comparison that we want. We want that to be greater than or equal to the demand that we have at facility D. Oops. So far, so good. So this is essentially, now we included the right-hand side of the inequality. And then, but we still have all of this stuff. And this is why I like to include all of this notation, is because it really encapsulates everything that you need to have in this generator statement and in the quick sum command. So we want this for D in distribution. And then I always like to name things. So this, what I have here now, this is the generator function. This is this is everything that needs to be in one set of parentheses. If you don't name things, and I'm gonna go to a new line so everyone can see things. If you don't name things, then I think it's okay to not have that stuff in parentheses, but I always like naming stuff. So we're gonna call this name equals meet demand. And we want to update so we can look at stuff, and there we go. So this is what pops out, is saying, okay, we have a constraint for Columbia, Indianapolis, for all of our distribution centers, we have this meets demand constraint. So now let's look at the other constraints that we have, which is the maximum production and also our minimum production. So what we have here in terms of the formulation, so now we're talking about each of these constraints must hold for the individual production facilities. The production facilities themselves have these constraints. So in order for us to get to that sort of level of index, we need to sum over the distribution centers. So everything that we send, or the widgets that we send to all across the distribution centers from a particular production center, that is limited by our upper bound, our max amount. So let's call the first constraint that we're going to model here. This is what we can produce. This is our and there we go, typing in real time. So similar to everything else, we need to reference the model, and we are going to add constrs. And since we're going to have another quick sum generator, so this is quick sum, and within that quick sum, we have our decision variable xpd. And again, since we're summing over the distribution centers right after the decision variable that we're going to sum over for D in distribution. Close that off. So this again represents the left-hand side of our inequality, less than or equal to max prod. And this is true for all of our production. So for P in production. Again, we're going to give that another name. That name is can produce. Oops, got to put that. Okay. And I'm going to copy the rest of the stuff so I can go a little bit faster. Oops, that's, you gotta making sure that you close off your parentheses is an important thing. And this should be good to go. There we go. So now we have, so this is showing, that hey, we have these constraints in there. So the last parts, the last of the major bits of information we have is our objective function. And we set that using set objective. Pretty straightforward there. So what we were told for this decision problem is we want to reduce the transportation costs. Well, the best way to reduce transportation costs is to minimize them, get them as low as we possibly can. So that's going to be our goal. So this is the notation that we have. We want to minimize the cost. So for each, again, this is our decision variable that relates the production facilities to the distribution centers. We have an associated cost, and we want to sum over all of those things. So for all combinations of production facilities and distribution centers or distribution locations, we need the cost times the decision variable, and we want that to be minimized. And again, in the interest of time, because my power went out, which was fun, just copy paste that real fast. So I'll give you a second to look at what we have here, and I'll go through it instead of just me fumbling along with typing it though. So let's start from the center in. We have our transportation cost, IJ. Oops, this should be a PD. Pardon me. So transportation cost PD. And actually, this would run, what I had initially would run fine. You don't have to call the index consistently. You can say I, you can say J, as long as it's consistent within the statement that you're typing up, it doesn't matter. So I'll just pretend like I did that on purpose as a teaching moment. So our transportation cost, PD, same as this value here, multiplied by XPD. It's our decision variable. And then again, immediately after that, we put what we're summing over. We're summing over both indices in this case. So this will be for P in production and D in distribution. And now that is set. So now we're done essentially modeling the problem. It is all of the bits and pieces are in there, all of the key components. But to be before we actually optimize, it's always good to make sure that that what you have in there is what you're looking for, and it represents what we have algebraically in all of our constraints and decision variables and objective and everything. So I'm going to minimize this for a second. Hopefully this goes well, and bring up what we call an LP file. And what we have right here is this command to write an LP text file. And let's look at what that looks like. This essentially is going to take our model, what we have right now, and put it in a nice text form that is somewhat easy to digest. So this is what the text file would look like. There's a lot happening here, but so it presents the name of the model that we're looking at, which is called widgets. And here's our objective. We want to minimize, and it actually writes out all of the coefficients times the decision variables, so you can see, using the names that we provided, so we can see exactly what our objective looks like. And here's, it's always good to sort of look, make sure, yep, this seems to be about what I have. If you're expecting, an objective or something that has, thousands of variables in it and only a few pop in there, then I'm like, oh, well, something's wrong here. So this is a great way to make sure that what you coded up earlier actually happens. This is what the model is seeing. So we have all of our constraints, our can produce constraints, our must produce constraints, our meet demand constraints. So things are looking good. So let's hop back to here. And this is, and additionally, there are other formats. There's a format called MPS, which doesn't have all the name goodness that we have, but it's a very easy way to share models, because you can solve something like that immediately. And you can do the same thing with LP files, but just MPS is a little bit more of a consistent format that people use. But it's a great way to, so the LP files, it's a great way to share what the models that you've created. And you might get a warning here, or you will get a warning for this, saying, oh, you have a space in there. The LP format specifically, that may give you some issues. So gurobipy is saying to use an RLP format if you want Gurobi to read it back, or you can use the MPS format, which gets rid of all the naming and just is very general. So let's actually optimize. That was fast. So what we have, let's take a quick look at the log here. A lot of this stuff you can just bypass right by. It doesn't really, as you get more experience with gurobipy and optimization modeling as a whole, this stuff will become more important. But the main thing is that it says it's solved. Congrats to us. And then what our optimal objective is. So essentially this is 1,704. We'll call them $0.89. That is our minimal cost. So now that we have that, okay, the next thing is, well, how do I get the solution? And we'll go through a couple ways. I tend to go towards the pandas way of doing things, particularly because we're a data analytics crowd here, data science crowd. Python folks, and pandas is, if it's not the #1 imported package, it's behind something like NumPy. And if you look at any Jupyter notebook, the first 2 lines are import, NumPy as NP and import pandas as PD. So I like to work using pandas as much as possible. It makes things nice to view and nice to work with, easy to manipulate and slice and dice your output data quickly from there. But that's not the only way, and we'll talk about a few ways. So let's take a second to digest what we have here. I'm not typing it out. This is already in there because it's not part of the modeling process, but it is important to understand what's happening. So we're looking at our model, M, and we want to get an attribute. And what we have here is we have two X's. And I did this kind of on purpose to make sure that, so I can explain the difference here. We call our, people like to call their decision variables X anyway, so I figured I'd take the time to describe this. So we have our lowercase x. This is our decision variable. This is our decision variable X. So if we called, if we called our decision variable at the beginning, like transport or ship or something like that, that's what would go here. And then this is what the attribute that we're getting is this capital X. That's the actual decision variable value. What pops out at the end. This is the optimal value for each of our individual decision variables. And then after this, so this is the gurobipy part of things, getting the attribute of the value from our decision variable. And then everything else here is Panda stuff. We want to name the series shipment, and then we're going to use the index, the transportation costs, so it all lines up nicely. So let's run this. And this is taking longer. There we go. All right. So now we can see our optimal solution for each production facility, what we are distributing to where. And I also incorporated the costs just so we could have that relationship as well and say, okay, well, yeah, our really high costs, they're not getting much activity, which makes a lot of sense. So this is what our optimal solution looks like. And there's a lot of zeros here. So you may want to think, well, I'm just really interested in the, actually, I'm gonna, instead of having run all this again, let's just copy this. So let's slice this by the shipment values that are positive. And here we go. So now we get the actual, like what is actually being shipped as opposed to the zeros. But so we could, this is our optimal solution, that this is the, if you were to prescribe this, you would achieve the value that the objective function says. So I think we have about a little over 30 minutes left. So I think we're pretty good. I think I caught back up to where I wanted to be pretty much at this point. Hopefully no more power outages for me. So a couple more ways to get the solution. You might be thinking, well, I'm not a big pandas user. I like dictionaries and things like that. Perfectly acceptable. And actually before I get into that, I hovered over something and it said, let's see, where was it? Here we go. I think it was this. Let's see if it pops up again. So our decision variable is something that we call, and actually it's a gurobipy sort of, it's a gurobipy thing called a tuple dict. So it's just a dictionary with multiple indices. So that's sort of what gurobipy transforms things into. And then, so when you see that term, just remember that that's a gurobipy specific thing. And it actually, there are ways to, there's a couple other pieces of gurobipy functionality that I sort of skipped over in terms of importing data and typing in data, hard coding data and stuff like that. That is actually quite useful, but I skipped over it because limited time, and I want to keep things in sort of pandas and whatnot. So let's run this. And if you look at what we have here, we want to loop through all of the, so I'm going to start here. m.getVars is, for this model, give me all the variables. And then, so we're looping through all of those, and then we're getting the value X, the dot X, which is the same as this capital X from before. I won't scroll all the way back up, but this is the value. So this is printing out essentially the table that we had before. And down here, this is more or less the same thing, but we are adding the conditional of saying, well, only print it out if it's positive. We don't want the zero, so this gives us the same thing as before. Same thing as before with the positive values. All right. So Actually, we may be a little bit ahead of schedule now. I think I went a little too fast, but that's okay. I have things up my sleeve. Solution analysis. So, all right, great. We have this optimal solution. That's good. You can present this and say, if you do this, you'll have minimal shipping costs, and everyone should be happy about that. But more information is, as soon as you hand that over to leadership, or if you're presenting this to people that you work with, they might be like, okay, well, I have a few other questions. So let's dive into the solution a little bit deeper and sort of help understand what's happening in the problem. So let's look at, what we don't know is how many widgets are each of these facilities producing. We know where they're going, and we could then, so to figure that out, let's just add things up. So we're going to group by production, group by our production facilities, select the shipment column, and just sum that up. And then I'm going to put that in a nice data frame that we're going to have the remaining, let's just do that first. So run that. Oops. There. So this is what all the production facilities are shipping out. And like, okay, great. Now that I know, okay, that some of these, Birmingham is behind, but you need to think of how does this relate to the maximum production for each of these facilities? Are there any leftovers? Is there any more space? If we needed to, if our demand went up by a little bit, are we still going to be able to satisfy it? And then also the utilization is important to us because we have this minimum. So it would be interesting to know which production facilities are at that min threshold. So now let's uncomment that, recomment this. And so we have a nice little data frame here that gives us a bit more of what's going on in our optimal solution. So Baltimore has 45 units that it can produce remaining from its maximum production capacity. Same thing for Charleston, we have 18, Cleveland, we have 14 units left. So this shows us that we have, if demand were to have a little bit of an increase, we're A-okay. We have the capability to meet that. And then the utilization, we see that Baltimore, remembering back to what our A constant was, the minimum proportion of the max production that makes our min production, that Baltimore is the only facility that is at that. So this may make you think that, well, if I were to relax that constraint, if I didn't have that, maybe this would be lower than that value in the optimal decision. And then, of course, if you were to relax that constraint, if you were to get rid of that, then everything would change because you have you have a new system that you're trying to model. So, so far so good. We have our optimal solution. We've gotten some insights out of it, and all right, still doing okay on time. So the values that we have here, this is what we would, you may say, oh, I have a little bit more slack in my system. So when you have an inequality constraint and the left-hand side and the right-hand side, if they're equal, when everything's said and done, which is happening for Birmingham and Little Rock, what they're producing is equal to their capacity, we say that that constraint is binding. So, it's at equality. If this doesn't happen, then there's what we call slack or surplus, depending on which way your inequality sign is pointing. But typically it's, we sort of call it slack a lot more often. So that is an important thing in mathematical optimization modeling and in formulating linear programs and things like that. So since it's an important thing, there's an attribute for it. So what we can run here is if we reference the specific constraint, which we named above, can produce, if you add the attribute .slack, it'll produce this value that's remaining. So let's run that. And then, so I'm putting that into a data frame and calling that remaining and calling this utilization. So it matches this pretty close. Let's run that. And ta-da, we get the same information. It's a little bit different. This is not in alphabetical order. Pandas puts things in alphabetical order here. So, so it's the same information. And actually a little bit, the calculation that we have up here is pretty straightforward and very simple, but sometimes actually calculating this out is a little bit more, a little bit harder to do than to type everything out. So just getting this makes it really easy to get that difference, between the left hand and right hand sides of an inequality. So far, so this is our main problem here, and we have a little bit more time. So this was done using continuous decision variables, and it just so happened that all of our decisions, let's go back maybe up here, the shipment values, they all happen to work out to be integer, which is great. Because you may be thinking, well, earlier on you said, well, we can't have like half of a food truck. That doesn't make sense. And it may make sense for your problem to not have half of a widget. And if that's the case, then at the very beginning, you can say, okay, well, let's make our decision variable an integer. But if that level of granularity isn't super important, then for a decent amount of problems, then you can just say, let it be continuous. And you may be asking, well, what's the big difference there? Why is that a big deal? In the next session, where Asan talks about comparing and contrasting machine learning and mathematical optimization, he gets into a little bit of why solving, once you introduce integer decision variables to problems, that it becomes a lot more harder to solve. So he's going to get into that detail as well. So if that level of granularity doesn't really matter to your problem, and it's okay if you have, a tenth of a unit or something like that, and or like a 0.01 or some fraction, if that makes sense for your problem and it's okay, then keep continuous, because it's just easier to solve. But again, if you need it to be integer, it can be. So let's scroll back down. So we just talked about, hey, this is we're using continuous decision variables that could be integer if it made sense. But we didn't use any binary variables. And again, to talk about what binary variables do, they're used in mathematical optimization for sort of yes/no decisions for switches, more or less. So let's look at looking at the solution that we have here, and actually, yeah, let's look at this solution. Remember this Birmingham location? It had a much lower maximum production. I'll just put that here, max prod, so we can look at it again. Everything else is, relatively high. Baltimore, Cleveland, Little Rock, all well above 100. Birmingham, not so much, only at 80. So let's say that that we have an option to expand that the capacity of that facility by either 25 widgets or 50 widgets, but there's a cost. So if I want to expand the production by 25 widgets, it's going to cost me $50. And if I want to expand it by 50 widgets, it's going to cost me $75. But you have these options on the table. And you may be thinking, okay, well, now I have to completely reformulate my problem. I need to start from scratch. I need all this sort of, that's the sort of the beauty of mathematical optimization modeling, is that we have this change to our problem, but it's not a huge change. And actually it just requires adding in a little bit, adding essentially another type of variable and another constraint. So what I'm going to do, what I'm going to do here is essentially define a whole new model, but it's going to have a lot of overlapping parts. So let's introduce a binary decision variable that is going to represent our two possible solutions. I'm going to call it xprod. So xprod 0 is going to be 1. Again, so this is a binary variable. Its only values that are going to take are 0 and 1. If xprod is 1, or xprod sub 0 is 1, that means we're going to choose the first option. we're going to expand by 25 widgets at a cost of $50. And if that is 0, then we're not going to choose that. If xprod sub 1 is 1, that means that we're going to choose the second option. We're going to expand by 50 widgets at a cost of $75. And if that value is 0, that means we're not selecting it. So this is allowing us a couple things. This is allowing us to not choose any of these. It may be still in our best interest if we're still looking at overall minimal cost. What we just solved may be the best solution for that. So what we're doing is we're introducing new options and saying, okay, are these new options going to give us a potentially better solution, a lower cost? So to start this model, let's first just sort of add the stuff that's going to be exactly the same. Let's define our new model M2. We're gonna have the same decision variables for the shipments. So, but now we need to make sure that we're referencing model M2, and the same as before. And our demand constraint is the same as before. So let's run that. One new thing that I added here. You may have noticed this, and I didn't notice this until I remembered, hey, I have this written here, is you may be thinking, if I'm adding variables and I know their coefficient, why can't I just add that right away? Why can't I say what the objective coefficient is right away? Well, gurobipy lets you do that. And that is with this obj argument to the add vars command. So we know that for each xij or xpd, we have a transportation cost associated with it. So if we say, well, let's make the objective that value, this takes the whole set objective command that we had before and having that quick sum there. It just automatically takes care of it right here. So we're essentially taking care of that line of code at this point. And we have our same meet demand constraint. So I ran that, good to go. Now we need to add the other constraints that are going to be a little bit different. And in the interest of time, I will copy and paste these and then go through some of this. Okay, a lot happening here. And let's do a little bit of, there we go, a little bit easier to read. So we still have our can produce and must produce constraints, our can produce, our must produce. The only thing that's different between this and the previous is we're keeping everything the same outside of Birmingham. That's the facility that we're trying to see, hey, should we plus it up? So we're going to look at for every facility other than Birmingham. So that's essentially what this is saying right here, for every P&P minus the element Birmingham. So to code that, we add in a conditional statement right after. So it really sort of follows this along. Again, remembering that the quick sum XPD for D and distribution, that's representing here, less than or equal to max production here. And then this is for the P in production, but only if it's not equal to Birmingham, which is what we have right here. And then the same thing for our must produce. And that's all good to go. Now let's add the new binary variables. And this I'll actually type out, called xprod, and that's going to be for our M2, our second model, we're adding variables. And another way that you can add variables is we have sets, things like that. We have our production facilities and things like that. You can just say, hey, I want 2 variables. And one way to do that is by saying range 2. So this is going to produce 2 variables that are called xprod. So that aligns to what I was defining earlier on. And let's look at here. I like how this popped up. The variable type by default is continuous. We don't want that. We want binary. So we need to say grb.binary. in caps. And then let's add the objective again while we're here. Objective is 50 and 70. Is that making sure I'm consistent here? 50 and 75, pardon me. And then let's call that, we're going to expand the Birmingham production. Okay, and there we go. Oops, I need the right name. There we go, it likes that. Important there that if you want to put a name, you need to actually call, you see name equals. Again, I did that on purpose as a teachable moment. So let's break this down a little bit. We used range n to add n decision variables. In this case, it's 2. We needed to change the type, the V type, from continuous to binary. We again used the objective command to immediately set the objective coefficients. And now this is our new decision variable. This is our binary variable. Again, going to be 0 or 1, and that we have right down here. So what we just created is, based off, because we use the objective functionality, we've already created the objective. We use the objective command, the obj command, when we're adding our variables. We already set the objective function, and that's what we have here. This is our previous objective function, the cost times the production at each individual facility. But now we also have 50 for if we decide to expand the production with our first option, and then plus 75 for our second option. And then but now the constraints for Birmingham specifically are different for the production, because we're still going to adhere by this rule of you have a maximum capacity, you need to make sure. So if we expand it by 25 or 50, that's our new limit. So we need to make sure that we're adding that. And then we're also going to respect this rule of, hey, you need to be 75% of your max capacity. Your business problem, your decision problem you may think, okay, well, let's just stick to the previous bound. That's fine, but we're gonna make it so that you respect the new lower bound. And all right, good on time still, but I will resort to copying and pasting because this is a lot here. The main changes between this, the code here and what we had before, obviously second model, but a lot of it is the same. We're summing over D in distribution. It must be less than or equal to the max production, but now we're adding in what production would be added. So this is our first option, xprod 0. If we select that, we're adding 25 capacity. If we select the second option, we're adding 50 capacity. And then the similar constraint down below. Both. So we're going to add a constraint once this all gets sorted out, saying that each of these are binary, 0 and 1, that we're only limiting ourselves to 1. So we can't have both of these options, but we can definitely have 0 of them. So we're going to sum over our x prods for I in the range of 0 and 1 for the two variables, and that must be less than or equal to 2. And we're going to name that expansion choice. So essentially now what would happen is we would run everything and let's see. Let me see if I can put this completed notebook here. So let's actually, we'll go a couple minutes over here and then fix the timing elsewhere.
And just a note for all attendees, we do have a 15-minute break during this session, so we won't be diving into any other content or disrupting the day.
Exactly. Thank you, Lindsay. So we solved this. Here's the proof that it was working. I'm not sure what happened, but that's okay. And we run, we get our optimal solution. And here we can print out the difference. So we have our first objective and our second objective. And then we can see that we do get a lower objective function from our second value. So that tells us that, hey, we selected something. You know, if we had the same objective function value, that means we didn't select anything. We didn't change the production value. So let's see what we did change. So in our second model, let's get the attribution of the value from our xprod. And we see that, you know, these were indexed by 0 and 1. So this was our first selection. This was our second selection, that we actually chose the first expansion. So our xprod 0 is 1, which means that we increased the production by 25 widgets in Birmingham. And that gives us a slight cost reduction. Awesome. And then let's look at the solution overall here. And we get, you know, you see that, okay, that the Birmingham, now we're up to, instead of having it's 80, we're at 105. So we're using all of that production as well. The new expanded production. So some homework, which is not really homework, but something that you can look into, and maybe we'll hit on this tomorrow, is let's analyze how the optimal solution changed between the two models. And when you do that, you'll notice something weird. You'll be like, that doesn't make too much sense. So think about what the weird thing is. What does it happen that is odd? And then think about, why do you think it happened? And then how would you address this from a formulation perspective, and then also a business problem perspective. So thanks for hanging in there and dealing with a couple hiccups along the way, one via electricity outage, one via something not working right in the collab environment, I'm assuming, and dealing with all of that. So check out the completed notebook if you want to see all the answers. We'll take a little bit of a break, and then we will start the next session in about 15 minutes. All right, thanks everyone.